In this lecture, we learn about the subchapter 5.5 in chapter 5. This one is explaining about the software-defined network control plane. What is software-defined networking? A little bit and briefly, we learned this one already, but in detail, we learn. Internet network layer and historically has been implemented by a distributed per router approach. That is so-called traditional approach, and traditional routers we learned briefly, and that was monolithic. That means single entity, single device, single equipment. That is monolithic router, and that is containing switch hardware, learns proprietary implementation of internet standard protocols, for example, IP and route information protocol, intermediate system to intermediate system protocol, and open shortest path first protocol. Also, as we learned, border gateway protocol. In proprietary router operating system, for example, Cisco's networking operating system is Internet Networking OS, so-called iOS. Same to the Apple's iOS, but this one was used first, and prior to Apple, Cisco used this one first time. That is Internet Networking operating system. This one is running in the router. This box is called middle box, and we are using many different kinds of middle boxes for different network layer functions. For example, firewalls and load balancers to provide some load balancing. Also, as we learned, this device, network address translation box. Those are all different boxes. But today's topic is how to integrate them together instead of using different and separate box, and using the software. Thus, that is called software-defined network, SDN. Actually, that was introduced around almost 15 years ago, actually 2004 or 5, and that was renewed after that and evolved. And Google is using that concept in Google's data center networking, that is people networking. And we'll learn a little bit about them together. Renewed interest in rethinking network control plane. There's how to make it simplified, how to make it convenient to deal with, just using software and with some common architecture in terms of networking, in terms of routing, and we learn. Let's move to the next. This one is explaining the previous concept, so-called traditional router. And in that router, that is called the per router control plane. Control scheme is embedded here, and those are different routers. Here, let's look at this one first. Individual routing algorithm components. In each and every router, this one is each and every different router. They are interacting with each other in control plane to compute porting tables. The main focus here is to calculate that porting table. For that porting table, we need to use some algorithm. In centralized way, we can calculate that one, or in distributed way. This one is calculating that, and that will update this one. And during that operation, to provide this porting table, this one is getting some information from other routers, and those information can be used to update that forwarding table depending upon that algorithm. That is called routing algorithm. And we need some protocol to interact with different routers, as we learned already by Cisco EIGRP or RIP version 2 or OSPF, and to cross-over some internet service providers border, we should use border gateway protocol, as we learned. Those protocols are mainly to get finally the updated forwarding table information and to update that entry. That is role of the control plane. And simply this one is using that given forwarding table to forward the arrived datagram here as soon as possible to the appropriate route for the final destination. This one also introduced, thus please recall. Let's try to recall. Logically centralized control plane. This means logically centralized. That means this one may be composed of a single computer server or several servers. It doesn't matter. Anyhow, that is centralized logically. Okay, let's read this one first. A distinct, typically remote controller interacts with the local control agent. This is local control agent in routers to compute forwarding table. And this one is interacting with this one. Also this one. Also this one. They are control agents. And they are logically centralized and integrated. They may be composed of different servers or in a single server, but conceptually and logically they are centralized. Okay, let's look at this one, software-defined networking, in more detailed information here. Why? A logically centralized control plane we need. That is easier network management, and we can avoid router misconfigurations, and this one is providing greater flexibility of traffic flows. There's some advantages. Because of that, we are trying to use this SDN and try to evolve and try to upgrade using this software-defined network. And that is table-based forwarding. And this is the standard and protocol, that is standardized protocol used for this SDN. Google is also using this one for their data center, using this SDN and this protocol, OpenFlow. And that was briefly, not in detail, introduced already. And that may be enough in our beginner's course about this computer networking. Recall OpenAPI, OpenFlow API, and this one is allowing programming routers with software, and this centralized programming that is easier to compute tables centrally and to distribute to the agent and to their switches. And the distributed programming, distributed programming, if we are using this one, then that may be more difficult. And this one is computing tables as a result of distributed algorithm or protocol. implemented in each and every router. Thus, this scheme will be simply applicable based on this SDN, and that is logically centralized. And we can implement based on the standardization, and that is called open implementation of control plane. And open means standardized worldwide, and that is not proprietary. In public domain, any company or anybody can use this one because that is worldwide standard. This term means open, means worldwide standardized, not proprietary of a certain company. Okay, let's think about some advantage. Probably this one is very important if we are considering the computer industry. Actually, that computer, in terms of the computer history, around at the beginning of 1940s, at decade, ENIAC computer was introduced. After that, 1950, 1960, 1970, 1980, at that time the PC was introduced, and Steve Jobs introduced the first time around 1976 until 1978, around that time. Apple computer using Rockwell CPU, that was introduced first time, and later around 1983, Microsoft's and OS and IBM's hardware, the IBM introduced a personal computer in the world. And before that, think about this one. Right after the introduction of that computer, IBM, they developed their mainframe, and mainframe 60, mainframe IBM 70, and due to their own proprietary operating system, OS, virtual storage, and their architecture, proprietary architecture, they introduced this kind of mainframe. For example, around the end of 1970s and early of 1980s, long time ago, for example. And also digital stack computer, and they announced the mini computer packs. They are all proprietary computer and the proprietary operating system they are using. And their market is not growing, not evolving so rapidly because of their limitations in terms of the growth of that market of the computer. That is the main drawback of this closed or proprietary architecture. And let's look at this one. Vertically integrated long time ago, like this, in the further mini computer and mainframe computer. Integrated, closed, proprietary, slow innovation, small industry. That is the main disadvantage of this scheme. Specialized applications, specialized operating system, specialized hardware. There are so many different kinds of. And that each one is not big enough in the market, in terms of market size. But that concept is moved like that. If we are using same architecture here, based on open interface, if those are standardized, then many third vendor companies are trying to develop, and they are very competitive, and only the lowest one and performance in terms of cost-effective architecture, cost-effective solution that will be successful in the market, and the market size will be growing so rapidly as we have been used already. For example, Windows operating system, Linux, or Mac operating system, or Unix, and different application vendors, they are providing the software, and each one will grow in the market rapidly because each one is taking the pie, big pie, and also the pie itself is growing, and it is the size is being increased rapidly. That's the main advantage of this scheme, open architecture based on some open standard. And also this CPU hardware, horizontal open interface, rapid innovation, huge industry. And Intel, think about Intel. And think about memory companies like Samsung or Hynix, SK Hynix. They are independently growing rapidly because of this scheme. And they are growing. And their growth is also helping other growth, and the whole industry will be growing and also evolving in terms of technology. That's the main advantage of this open architecture. Third, that concept will be used in our software-defined network to provide networking devices, including router, as well as many other NAT or many other different kinds of load balancer, and we learn. Let's think about this traffic engineering. Here, even for this traffic engineering, it was difficult using the traditional routing scheme, traditional router. Question is, let's look at this question first. What if network operator wants use U to G, U from U to G. U is here, J is here. Traffic to flow along UVWZ, UVWZ, and to flow X, W, Y, Z. To flow, that is, answer is here. We need to define link weights so traffic routing algorithm computes routes accordingly. Thus, that means U2 current and the previous traditional routing algorithm cannot do that, cannot deal with this kind of requirement. One needs a new routing algorithm, and it is difficult and complicated. Thus, for the traditional router, the schemes are based on link weights, and that was only unique control button or control knobs. That was not good. Also, this is another requirement. Also, that is impossible. That is not possible due to previous traditional router. Okay, I'll use this one. What if network operator wants to split? In terms of traffic engineering, the traffic should be divided here. One is here, and another should be here in that stream direction. U to Z, still the destination is same, but on the way, we want to use two different routes in terms of the traffic engineering, because we want to divide that traffic. That is called load balancing. One is here, another one is in this route. Then the traffic will be divided. We cannot do that. Well, we need a new routing, complicated routing algorithm. And also that is difficult or not possible. Thus, why we need software-defined network instead of this traditional scheme. Also, another requirement that is also difficult due to the previous traditional routing scheme. What if W wants to route, W here, route blue and red traffic. Some traffic that source is from here, then that should go this direction using this link. And from this one, that traffic should go, and this Y, that should be the intermediate router on the way. And also this is not possible. With destination-based porting, our previous and traditional routing scheme is simply destination-based porting. And link state and distance vector routing, we cannot do that. Now, this is the SDN. To introduce this one, we just thought about some requirements and some possibility and the difficulty based on the previous traditional approach. Instead, if we are using this scheme, software-defined network, even though that scheme was briefly introduced in the previous lecture, this one is introducing a little more in detail, but not very detailed. Okay, programmable control applications. The architecture is layered like that. This one is control applications. There's a routing application, access control application, load balancing application. And okay, let's look at this one first. Following this number, generalized flow-based porting. For example, open flow standardized and protocol, open flow protocol. We are using this one to send some message to update that flow entry. We are using that. And number two, here's number two here. This one is control data plane separation. Conceptually, we divided already. Above one is control plane, and below one is data plane, as we learned already. Conceptually, we learned already about this. What else here? Control plane functions external to data plane switches. Okay, this one is independent from this one, anyhow isolated, and they are logically centralized, as we learned. There may be many network control applications like that. And this one is programmable control applications. And they can be independently developed. And they can be evolving independently. And also the market will be growing independently. And many third vendor companies can provide their solution in the market. SDN perspective. First, let's look at this part first. From this bottom, and let's go up, bottom up. This side is data plane. Okay, let's use this one. Data plane, software-defined controller switches. And this one is explained about data plane a little more. And this data plane switch, this one, this switch, that should be fast, specialized only for switching based on that given flow table. Fast, simple, and commodity switches implementing generalized data plane porting in hardware for their high performance. And the switch flow table computed installed by controller. That table entry, they will be computed and installed by this controller, as we learned briefly in the previous slide. And API for table-based switch control. Then how? This one is providing some message and some required information will be given to this one. to get the proper and appropriate flow table information, defines what is controllable and what is not. And also we are using open flow protocol. And protocol for communicating with controllers, this one is explained about that. Open flow standardized protocol that is being used for that communication between this body and this body. And that will be explained a little more in the next slides. SDN perspective, still we are learning about this. Now about SDN controller. Here we are learning about SDN controller. Still we are learning about SDN perspective, but we are focusing on that SDN controller here. This one is control plane part. And we are calling this API is, think about map. This bottom side is south. Thus this is southbound API, and the upper one is called northbound API. And this one is SDN controller. And network operating system. And network control applications. Later we'll learn about this one. This one and this one. That is called control plane. This control plane is composed of these network control applications as well as this SDN controller. Here let's focus on this SDN controller, network operating system. This one is maintaining network state information. And this one is interacting with network control applications above one, this one, by a northbound API. Always we need some API to interact. Also this southbound API to interact with this one. Well, this one, with northbound API. And below one by a southbound API. And implemented as distributed system for performance. Even though that is logically centralized, that can be implemented as distributed system for the performance and the scalability and the fault tolerance. That is for reliability and robustness. But conceptually, logically centralized. Here, let's try to focus on that the control plane. Here, the network control applications for the router, previous router that is doing this routing functionality. For firewall, if we are considering firewall, then that is doing this access control, also network address translation, and many other applications maybe here to provide some load balancing. Load balancer may be used, and those applications can be here, and still that is composing. They are composing the control plane. And let's read this one first. Network control applications, that they are the brains of control. And they are implementing control functions using lower level services and API provided by SDN controller. Here, this one is being used. This is northbound API. And they are unbundled. That means independently by each third vendor company can sell this one, and each one will be growing in the market. Okay, this unbundled. Think about our PC industry. That industry is unbundled. Hardware independent from software, right? Software vendors. They are not bundled. A long time ago, they are bundled together. But now it is unbundled in the same way. This one can be provided by third vendor company or third party, distinct from routing vendor or SDN controllers. Components of SDN controller. Let's look at this middle part. This is either SDN controller, and that seems to be a little bit more complicated than other block. Here, many blocks. And let's look at this one first. Interface layer to network control applications. This is interface layer, and the middle one is network-wide state management layer. And the bottom one is communication layer. And this OpenFlow, as we learned, this protocol and the standard protocol is being used here. This one is mainly to communicate between SDN controller, this one, and control switches to get some information or to provide, to update that table. We'll look at some messages later, and also some network management purpose, simple network management protocol that is being here. This layer is communication to from controlled devices and communication layer. And the middle one, this one is network-wide state management layer and state of networks, links, switches, services, and a distributed database about that information. And this one is providing network-wide distributed and robust state management. And the link state information and those are being used to apply that algorithm based on this information and switch information and the statistics and pro tables. And above one, this one is interface layer to network control applications. To this one, interface abstractions for network control applications, network graph and the RESTful API. That means over the HTTP. Okay, this one is introducing a little more about that the OpenFlow protocol, a little more in detail. This protocol, OpenFlow protocol and the standard protocol, this one is the controller for that, using that standard. This one is operating between controller and the switch. There's some protocol to exchange that information, to provide that table entry, and to get some port or link information, to apply that current status of the link in the algorithm. Those information can be provided. Those are all based on this OpenFlow protocol. And here TCP is being used to exchange messages. Optionally, we can use encryption for security. Also, that is very important. Three classes of OpenFlow messages. One is from controller to switch. This controller to switch. And asynchronous, switch to controller. Also symmetrically. Miscellaneous. First one, controller to switch message here. From this controller to switch. What kind of messages are there? This one is showing some messages from here to here. Key controller to switch messages. Features, controller queries, switch features, switch replies. Asking, and this one is answering, replying. And configuration. For the purpose, configure, controller queries, set, switch configuration parameters. And modify state, to update or modify, add, delete, modify flow entries. This is porting table in the traditional routers terminology. And here in software-defined network, we are calling this one program entry. This is same to the coding table entry, but here this one is generalized one. And the packet out. Controller can send this packet out of specific switch port. This is controller. Some switch port, the packet will be sent out. And this one is the center in terms of the in and out. This one is out from this one, out. And this one is getting that information, then that is packet in. Next one is explaining about that. This one is in reverse way. The direction is different from switch. Okay, let's try to use this one. From switch to the controller, what kind of message can be sent? Packet in, as I just mentioned. This direction is in. And if this one is coming out, then that is called out, packet out. Packet in, transfer packet to controller. That's different from this packet out message. From controller to this. That is packet out, but this one is packet in. Flow removed. Flow table entry may be deleted later if that is not used anymore, expired. Then also that is removed. Flow removed. Flow table entry deleted as switch. And port status, also that information is important. This link is disconnected, and that information should be given to this controller for updating that flow table entry. Fortunately, network operators don't program switches by creating, sending open flow messages directly. Instead, use high-level abstraction at controller. And this one is explaining a little more about that here. This one is showing that sequence using the sequence number here in that order. Okay, let's follow that sequence number. First, let's assume this link was running well, but later it was disconnected. Problem. Thus that information is given like that. S1, experiencing link failure using OpenFlow port status messages to notify a controller. As we just learned, from this switch to the controller, that will be reported. And SDN controller receives OpenFlow messages. This one is explained here. Updates link status information. That information, link state information, that link state is being changed because that is disconnected. That will be updated. After that, this extra routing algorithm is using those information to get the shortest path using that algorithm. This application as previously registered to be called whenever link status changes. If there is any change, then that information should be used in this algorithm. Thus that is being reported like based on interrupt. Why it is called. Number 4, after running that routing algorithm, Dijkstra's routing algorithm, access network graph information, link state information in controller, computes new route. It is computing new route. Then next sequence number is 5. That will be given in this way. Number 5, link state routing application interact with the flow table computation. component in SDN controller which computes new flow tables needed. And that information will be finally, this controller uses OpenFlow to install new tables in switches that need updating. And that information is given to here in this flow table, and that entry will be updated because that is disconnected. And thus from here to S2, that can go through in that way. It cannot go directly. Also this one is using this one to go to send to S1. Okay, think about these challenges, some of that challenges. The selected challenges let's look at. Hardening the control plane. That is not firmly completed. Thus we need to make it more stable, and in terms of the dependability and reliability and performance scalability and security. And that should be robust, and we should consider the robustness to failures. This one is leveraging a strong theory of reliable distributed system for control plane, and we should think about that dependability and the security. And that talks protocols meeting mission specific requirements. We should think about that also. That is for real-time application, ultra reliable and ultra secure applications. We should support them. And also we should think about internet scaling to use in our infrastructure. This one should be hardened more, and later that will be advanced more and developed more. We can use in our infrastructure more. Okay, this is the good point to wrap up today's lecture here.